Okay, guys. So I'm audible to all of you. Audible, right? I'm audible to all of you. Okay. So in today's session, we will start ISRO 2017. In 2017, there was twice ISRO conducted the examinations. You know, so set one we are doing. Set two we'll do in the our next class. So in this one again, we are going to cover strength of material, machine design. Now, when you look at the first question, okay. So what they have given the beam is fixed at one end. The beam has given at one particular end, and at the other end there is a propped support, right? So you know that this is nothing but propped cantilever beam, right? This is the example of propped cantilever beam. Propped cantilever beam. The beam is fixed at one end. Let's say this end is A, this end is B, and it might be subjected to this is nothing but vertically supported at the other end, right? There is a vertical support. So now how many reaction force will be coming? One reaction force at B, that is a vertical reaction force. Other vertical support will be here at the fixed end, and there will be certain movement also. There will be movement also which will be acting, resistant movement. So for a vertical load, this beam is fixed at one end and is vertically supported at the other end. Note on the figure. And there might be certain load somewhere it might be acting. We don't know, but there will be certain vertical load, right? That must be acting. So how many reaction forces are there? The number of reaction force, the number of unknowns, RA, RB, and resistant moment. There are three unknowns are there, right? Three number of unknowns are there. How many static equilibrium equations are available? How many static equilibrium equations are available with us? The static equilibrium equations are summation of forces in the y direction to be zero. That is the one static equilibrium available. In that case, Ra plus Rb, that is equal to P. And then we have summation of moment about a point, about any point that is to be zero. That is another static equilibrium equations. So we have two equation which are available, right? Number of static equilibrium equations available will be two. The number of static equilibrium equations are available is what? Two. So the degree of indeterminacy will be how much? Degree of indeterminacy will be number of unknowns minus number of static equilibrium equations available. That is 3 minus 2 will be what? 1. So the correct answer for degree of statical indeterminacy will be 1. Right? Make a note of it. Because we have another equation, static equilibrium equation, that is summation of forces in the horizontal direction to be 0. But any use of this static equilibrium equations, there is no use of that. Because there is no horizontal external load. There is no horizontal external load. Then why we will use this? Even though you use that, it will be irrelevant for us. That is a redundancy of using these equations. So only useful equations, rather to say number of useful static equilibrium equations which are available is only what? Two. Summation of forces in the y direction is zero. Summation of moment about point A, point B to be zero, right? In those circumstances, we will see that the number of static equilibrium equations which are available is only two, and the number of unknowns are what? Three, right? If this question would have been asked for a general loading case, then what will be statical degree of statistical, statistical indeterminacy? If this question would have been, let me explain in the next page. Suppose now the load is acting at an angle 60 degree, for example. Now, for a very general loading case at a point B, let's say the distance is L by 2, L by 2, A, B, C. Now, how many number of unknowns are there in this circumstances? The number of unknowns will be here. There will be, there will be horizontal reaction force, vertical reaction force. There will be vertical reaction force here. There is a vertical moment will also be there. But there will be moment will be acting, resistant moment will be acting at a point A. And there is a general loading case P. Why there is a horizontal reaction HA will be coming? Because if you resolve this particular external force, there will be P cos 60 that is acting in the horizontal negative x direction. So in the negative, in the positive x direction, there must be some support reaction force must be coming. Then how many number of unknowns? The number of unknowns will be 1, 2, 3, 4. And number of equations will be 3. Then again degree of indetermination will be what? 4 minus 3, that is equal to 1. Still it is statical, statistical indeterminate beams. Still it is indeterminate beams. Propped cantilever fixed at both the ends, all are what? Statistical indeterminate beams. Statically all are what? Indeterminate beams. Statically indeterminate beam. Statically indeterminate beam. Moving on to the next question. Two bolts are there. Two bolts. In the bolts, we know that there is a sank portion and there will be threaded portion, right? There will be sank portion and there will be what we call threaded portion, right? Here, this is nothing but threaded portion. Sank portion. We also call unthreaded portion. This is a bolt head, right? So now when you look at the, and now it is being subjected to tensile load, for example. They are asking what is the strain energy because of the axial load. Because of the axial load, we know that strain energy will be P square L divided by 2A. There are two bolts, A and B. What they are giving in the problem, strain energy which is stored in the bolt A will be 16 times bolt B. Load is same, length is same, only the area will be changes. Whatever the mean diameter is there, that mean diameter will be changes, right? So here there is a 2A, E. So here, if you just consider this is for A, 16 times. 16 times of what? P square L divided by 2A of bolt B. P is same. Both are subjected to what? Identical tensile load. See that? Identical tensile load. PA is equal to what? PB. That is equal to P. So this will cancel out. Length And material E and L will also be same. Only area will be getting changed. So area of the bolt B will be 16 times area of the bolt A. That means, can I say diameter of the bolt B, as we can write pi by 4 dB square, 16 times pi by 4 dA square. So can we write dB will be what? 4 times dA. Or here we can write diameter of the mean diameter of the bolt they have given. See, we have outer diameter, we have core diameter. Generally, in case of when what we say, in case of threaded bolts, whenever we talk about the tensile stress, actually it is being introduced at the threaded portion here, right? So, you might be thinking, sir, why we are not taking the core diameter? In the problem, they said that you have to take, for calculation of the strain energy, we have to take mean diameter, right? So mean diameter is basically what? Outer diameter plus core diameter divided by 2, right? So here it will be 52 mm. A will be correct, right? See, this is the outer diameter. This would be the core diameter. Whatever this is there, that is the mean diameter. We sometimes we also call that is a pitch diameter, right? Now, this is the another problem, one of the good problem from strength of material. In this particular problem, they have given initial diameter 12 mm is tested for a tensile strength with the gauge length of 50 mm initial length. Final length they have given as 80 mm. Final diameter is given as 4 mm. The load at the yield point they have given 1130 Newton. What is the nearest yield stress and percentage reduction in the area will be what? So one of the good problem. So they tested whether you know the stress strain curve correctly or not. See, now some of you might be thinking, sir, here they are asking what is the yield stress when we plot the graph, or let me tell you in the next slide. See, solving the previous problem just like a robot will not help you. Again, I'm repeating you. And those who are thinking the written examination is just you know easiest thing we can get in ISRO, then you are fooling yourself, right? Only solving the exam previous year problem will not help you. You have to understand why they have given the problem, and behind that we have to solve thoroughly, not just like a roughly we have to solve. No, let's say we are talking about ductile material. For ductile material, there will be some initial part of the curve, and then there is some plastic deformation will begin. This is the engineering stress strain diagram. What we are observing is engineering stress strain diagram that we obtained from original diameter. Original diameter, whatever the original diameter was there, that we have considered for calculation of this stress at individual points. See that this point, all are based on the original diameter. But generally, there is a deviation from this stress strain with the true stress strain diagram, something like this. It will be start deviating from this point and it will be continuously increasing like this. So this is nothing but true stress strain diagram. That was based on the uh, instant cross sectional areas which are available. There will be necking, there will be, you know that when you start loading the material, there will be certain amount of necking will be there, right? There will be necking. When the necking will start, area will be suddenly reduces. So here, whatever you are assuming that we have to reduce the load to get the maximum fracture point, right? There, why the curve is getting flattened, right? In fact, some of the cases you will observe the curve is basically getting reduced or decreasing. Stress will be decreasing, but generally it won't happen in reality. In true stress strain diagram, actually it is being increasing because area will be decreasing and decreasing, and you know that stress will be what, load divided by instantaneous area. So area will be start decreasing, so stress will be start increasing at a very rapid rate. In the problem, they have not mentioned anything. What is the nearest yield stress they are asking? So generally, the difference between the true is till the elastic limit. When we work with the when we work within this zone, then there is a no difference between true stress strain diagram and engineering stress strain diagram. All are almost like the same thing. It will follow the same curvature, but the deviation will be started when the yielding will be starting taking place. So definitely, whatever the true value of the yield stress will be there will be different from engineering yield stress. Remember this fundamental rule right now, which I'm telling you, that whatever is given in the problem, whatever they will be given in the problem, no doubt. Even this will help you in production also. Whatever given in the problem about stress, that stress will always be engineering stress strain. That will always be what, engineering stress. Whatever given the problem, even they might have given the strain also. That means they have given engineering strain. If they will be asking, or whether they have given any yield stress, that means they have given engineering yield stress. Means indirectly they are asking engineering yield stress. And you know that what is the engineering yield stress? What is the load at the yield point, and what is the original area? Because we are not bothering about the instantaneous area, we are only bothering about the area which are available at that particular point, that to original area which are available at that instant is not at all useful for us, right? So in this case, when you calculate 1130, original area will be pi by 4 d square. D diameter is what, initial diameter is what, 12 mm. So when you calculate, you will be getting 9.99 MPa. That is almost like 10 megapascal. That will be the answer. The next thing, whatever the question they ask, that is a very simple thing. Percentage reduction in the area. So AI minus AF divided by AI into 100. So that is pi by 4 d square minus pi by 4. What is the final diameter? Final diameter is 4 square. Again, pi by 4 d square into 100. So when you do that, you will be getting 88.88 percentage. So means approximately 90% we can say. That means 10 and 90. C option is correct. So these are the small things which we are discussing. Please make a note of it. Right. So actually it is being picked and then it is getting dropped. So generally, I talked about the mild steel, that is a low carbon steel, the graph which I have drawn. Okay, try to solve this question. What will be the answer for this question? Spherical joints, right? Spherical joint. Joint means two members will be there, right? So generally, if I take a joystick, for example, and if I placed it on a particular surface, a joystick, this is the member two, this is the member one. Pair means there has to be two element, right? This particular question is belonging to theory of machine, right? So spherical joint means there has to be two member. One is a particularly joystick, you can see, and second member is a joystick, and first member is a ground plate over which you have placed it. So now tell me, degrees of freedom means how many motions are possible for this particular joystick. You know that if I consider this to be y, and if I consider this to be x, and if I consider this to be z, you know that this joystick can able to rotate about x-axis. Joystick, joystick, the by means of which we play the games. So here it can rotate about x direction, it can rotate about y direction, it can rotate about z direction. Three rotational motions are possible. When three rotational motions are possible, my friend, then we say it has 3 degrees of freedom. There is a no translation motion is possible, only it can rotate. Joystick can able to rotate only, that's it. So what should be the answer? 3 should be the answer. More detailing about the degrees of freedom, what are all the spherical joints, types of spherical joints, or maybe example of spherical joints will be discussed separately in theories of machine. Here, this particular question, a fatigue strength of for a non-ferrous material is usually defined at a stress cycle how much? Generally, see, in the last class also I talked about the fatigue strength. Let me discuss some few more points regarding the fatigue strength by these questions. So those who want to understand actually what is the meaning of fatigue strength, and so let's discuss something about endurance strength or fatigue strength through this example. Okay, so let me explain this endurance limit, fatigue strength, endurance strength, what we mean, and then we will say what will be the you know deciding thing, like how we decide for ferrous material and for the non-ferrous material. Now, understand. Here, we will talk about the endurance limit or strength. I have discussed, but once again, I am discussing because this is very important and they will repeat once again. Right? So, note down. It is defined as it is defined as maximum value of the it is defined as maximum value of the maximum value of the completely reverse bending stress, completely reversed bending stress that a material can withstand, that a material can withstand, that a material can withstand for a finite number of cycle, for a finite number of cycle, or we can say for maximum value of the completely reverse bending stress that a material can withstand for a minimum life of 1 million revolution, 1 billion revolutions. At least, see, when we say the minimum value of the, or we say what is the maximum value of the bending stress that a material can withstand to complete at least infinite number of cycle. When we say infinite number of cycle, it doesn't mean that we talk about infinite number of revolutions, right? When you take example of shaft, when we take the example of shaft, I told you the Wallace, that is a German engineer, those who conducted the experiment for determining the value of endurance strength. What he done, he has just taken the specimen, he has taken the specimen which are of the this particular shape, and it has been supported. Here also it has been supported. This he has connected to one motor with the help of coupling, and here he has connected to one counter. uh, Basically one revolution counter is there, and this he has subjected to some kind of loading, let's say wi, or we say w1. At the middle of that, you know, and okay, other dimensions are given in the particular these are the standard specimen. What he has done, he has taken the standard specimen. This standard specimen is a polished surface, very, very mirror like a surface. There is a no defect and all. In reality, we know that there is a defect, but in this case, there was a no defect at all. And certain dimensions he has taken. He has taken the length, the total length he has considered from here to here. The length of that specimen was 87.5 mm, and the radius what he got was 25 mm. Here, whatever the radius of curvature he got it, that is 25 mm. These are the standard specimen he has considered, right? Once the load he has applied, that is the W1 load he has applied, then he calculated the bending stress. You know that this point A, after every revolutions by 90 degree, let's say the shaft is being rotated by 90 degree, we know that there will be there will be what? Completely reverse bending load must be acting like this. For this, you know, this is what we have stress, and here we have number of cycles. Remember, one cycle, one revolution of the shaft is equal to one cycle. One revolution of the shaft, one revolution of the shaft will be what is considered as one cycle. One cycle here. That whatever the counter will be there, that revolution counter, it will just note, basically note down the values of number of revolutions before failing the component. But how many components gonna fail? How many components gonna fail? then we consider, or then we note down the values. When we note down the values, for example, the bending stress, we got maximum value 32 m divided by pi dq. M is what? M is, we know that wi L divided by 4. WL by 4. As Wi will be keep on increasing, the bending moment will be keep on increasing, the bending stress will be keep on increasing. Right? That is the one thing we know. Suppose there is a 40 shafts are available with us in the first round of the, doing this experiment. Out of the 40 shaft, we generally take 50% reliability. What is the meaning of 50% life? L50. We generally define the bearing life in terms of this, what we call the fatigue life for 50% of the reliability. That means out of the 40 shaft, the moment 20th shaft gonna fail. One shaft fail, second shaft fail. Till that we wait and wait. We will wait. We will wait. We will wait, and we will continue wait till that 20th shaft gonna fail. The moment 20th shaft will be failing, then we note down number of revolutions that is made by the whatever the shafts are, the number of revolutions that is made by the shaft, and that we note it down something like this. So here we plot stress and the number of cycles here n. So for correspondingly this amplitude of the bending stress, we have noted down that these are the number of revolutions that we getting. That is L50 for first round of the setup. Some after that, what we have done, we have reduced W1 loading, and then we calculated again the bending stress, and we got to know that it has been reduced. When it has been reduced, you know that now it will take more amount of time to fail 20th shaft. Again, for the second round of this particular game, we have taken 40 shaft, and again we waited for 20th shaft to fail. And before that, the moment it is going to fail 20th shaft, then we noted down the number of revolutions, and we got to know it has been increased. And this is the L50 life for second round of this total shafts. How many number of revolutions, number of rotation has been made by the shafts that we are rotating at that time. Now we keep on reducing the Wi till sigma E. That means we keep on reducing, keep on reducing, keep on reducing the value of load in such a way that now the bending stress is equal to sigma I. That is, it is just equal to endurance limit. What is the meaning of endurance limit? Here, when we start reducing the load, the number of revolution will be keep on increasing, and we will reach certain stage where it will complete 1 million revolutions, 10 power 6 cycle. So what you are observing, that this graph is nothing but what is becoming what? Asymptotic graph. At 10 to the power 6 cycle, the moment 1 million revolution cycle is there, it has become what? Completely flattened. Asymptotic this will become, right? The moment you are applying further, you are reducing the load. Let's say you are reducing the load. Now you are having the amplitude load. Amplitude. What is the meaning of amplitude? Stress amplitude. I told you in the last class. Variable stress. What is the meaning of variable stress? Maximum stress minus minimum stress divided by 2. You know that the maximum stress is what? Minus of minimum stress. That is the bending stress, maximum bending stress, right? Now when you put these values, what you will be getting? Bending stress only you will be getting. Now when you reduce further this bending stress to below this endurance limit, you will be getting that even though you just apply 5 megapascal plus 5 minus 5 plus 5 minus 5 plus 5 minus 5, you will be getting infinite number of cycles. That means you just rotate the shaft and you just come back after 10 years, you will see that shaft is still rotating, it is not failing. Again, the shaft is having infinite life. It doesn't mean that you are coming after 100 years and you will see still the shaft is rotating. No, that means sufficient amount of time you have allotted for the shaft to be, say, it is not failing. That means, let's say, 10 years. That is the infinite number of cycles. That means the graph will become asymptotic. The moment you reach endurance limit, it will make 1 billion revolution. Below that, it will make infinite number of revolutions. And how we define endurance limit? We say that if we are putting the shaft for transmission purpose, the cost has to be justified. When the cost will be justified? When it will complete at least 1 million revolutions. There we define endurance limit or endurance strength of a component. Just like what we define yield stress in a UTM testing machine, similarly, this test has been conducted to determine endurance strength. But put a note and note down. Just like what we have, yield strength is a property of the material, but note down endurance strength is not the property of the material. Is not the property of the material. Ultimate strength, yield strength, these are the property of the material, but this is not the property of the material. Now in this question, they are asking the fatigue strength or endurance strength for the non-ferrous material is usually defined at how many number of cycles. This particular graph we have plotted for ferrous material. For ferrous material, generally for the non-ferrous material, my friend, generally for the non-ferrous material, this graph will become asymptotic at 10 to the power 7 cycles, right? When it will just complete 1 crore revolutions, then we say here sigma versus n graph, when we plot, it will be like this. It will be just become asymptotic at 10 to the power 7 cycles. Make a note of it. Actually, when you talk about the non-ferrous material, we don't have any fixed value of the, you know, number of cycle at endurance limit, right? This is the endurance limit for non-ferrous material. But what I'm telling to you is that for a non-ferrous material, just like a aluminium, examples are what? Aluminium, or some other examples. You can talk about some other than iron material. You know, when they ask for this type of material, there is a no fixed value. These are the approximate values. Note down. These are the approximate values. These are not the very fixed values, right? This material do not exhibit, this type of material, this type of non-ferrous material do not exhibit a distinct value, a very unique value of the endurance limit in a true sense. But still, the fatigue strength of this material is usually defined at a stress at a particular 10 to the power 10 to the power 7 stress cycle, where it will complete 1 crore revolutions, number of rotations. Then we say during that moment, whatever the stress is there, that we say endurance stress or endurance strength of a component, right? Because for the ferrous material, it usually become asymptotic at a cycle of 10 to the power 6 cycle. But for non-ferrous material, at 10 to the power 6 cycle, it has certain slope. It is not become flatter. I told you when to determine the endurance strength, when you can determine any for any component, right? For any component, when you can determine endurance strength, when the curve will become asymptotic. When the curve will become asymptotic, at that particular point, whatever the number of cycle is there, whatever the
You are currently the only person in this conference.
I was aware, but suddenly. Mhm. Yeah, yeah, yes, yes. Mhm. Yes, 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 yes. Just now it has been stopped, right, sir? Okay, okay, okay. Okay. Yes, yes, yes.